Okay, so this is a separate project. This is my automaton compiler. Basically, like when we were in class today, Simon had his similar thing. Mine is, I've done basically the same thing. The difference is that the syntax that I'm using is like the mathematical formal definition of a DFA. So we're like giving it like what you would ask with like, give us the formal definition on a test. So we're basically doing that as an input, and then we're doing this. So we can test a string, like we're gonna test this string. Run, reject it because it did not have. Let's do 111, and that's accepted because it's odd. If we do another one, reject it. So we can have this other. This is like an enumerator mode. We're gonna do up to length 8, and it's going to print out basically all the strings that are accepted up to length 8. Let's do it a little smaller so that we can confirm that it's working properly. You see like 1 1 1 1 1 1 3 1 1 1 3 1 1 1 3 3 3 1 1 1 3 1 3 3 3 1 3 3 3 3 3 3 5. So no even number of ones. That's about all. The NFA is basically the same as the DFA, but the PDA is basically an extension of the NFA. So let's actually show the PDA. This one's a little bit complicated. The reason why it's complicated is because of the non-determinism. The way I've implemented this is I have basically like a list of or a set of states that it's in, where each state is defined as the pair of a state and a stack. So we give a pair of a state and a stack, and then using the Cantor pairing function, we can get a perfect hash for this, and then we can get this to work. So this is the, what is this, 0 to the n, 1 to the n? Let's try 0 0 0 1 1 1. Build this and run it. Hope we have to change, and we accept it. And we're just using basically sets, and we're just unionizing them to maintain a set of all of the parallel like computations we're doing at the same time in a single thread, and that's what we're doing. Let's do up to let's do 12. You see, it started to take a little bit longer because there are a lot of strings that it's rendering and then rejecting. So that is the 0 to the n, 1 to the n. Here's a modification of this for, what is it, even palindromes? Yeah, even palindromes. Let's do up to length 5. And those are the even palindromes up to length 5. Okay, so that's pretty cool. And we also have a Turing Machine mode, where it's very similar, but now we have a Turing Machine. And this Turing Machine is what? Word. So this one is unique in the sense that when we test an input string, we're also going to get an animation. So let's try this. We can speed up our Turing Machine animation. Hey, look at that, we got rejected. Let's do like 1 1 or 1 1 0 1 1 0 0. That's fine. That should work. Accepted. Hey. Okay. And we can enumerate this. Let's do up to length 20 and run. And then you can see like all these things are being output into this box here. This is like, I made this specifically when I was doing homework and I wanted to debug my Turing machine to make sure it worked. So then I made this parser and thing, and then I ran this on it, and you can like look at them and confirm that these are in fact all word. So that's kind of cool. And we can also, here's another, this was one that was on the midterm. What is it? What should we test? This is what, twice as many ones as zeros, so let's do 1 1 0. And then we can run this. And we're just padding the ends of the string first, and then we're going to a state where we're going to move all of the zeros onto the right side. right? And then once we do that, we pad the end with a hash to mark the end, and then we go through, we delete a 0 and we delete 2 1s. Oh, I have to edit this out now. Okay. Let's do that again. Okay, I did. Okay, whatever. Here's A to the N, B to the N, C to the N. Right, A, B, 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 C, C, C. It accepted. And you can kind of, this is more of, not a formal proof, but here we're just testing a bunch of input strings to see. And hey, we got, it works on all of the ones up to length 10. Will that work for everything? I don't know, but close enough. And let's actually do the same thing for twice as many ones as zeros. Do it a little smaller. Maybe a little bigger than that. So 4 2 4 2 4 2 4 2 4 2 4 2 4 2 4 2 4 2 2 1 2 1. Okay, that seems to be working good. Yeah, and there's a whole lot more the bigger you get. So I think that's all on this front for this project that I've done. That's about all. Goodbye.